Please welcome to the stage, Nico Waisman.
Hey everyone. Can you guys hear me? Yeah, you can. How are you guys doing? First of all, thanks for staying with me. I know it's very late. I am super tired, and I'm sure everyone else is burned out by now, like so many talks. So this is why I have this slide over here, not this one, the other one. Oh, what is my first slide? Well, anyways, so open source security. Vulnerability never came along. This is going to be the corollary of my presentations, that vulnerabilities will never come by themselves. There's always more than one in a code base. And so before we start, let me introduce myself. I'm the guy on the left. The other one is a pigeon. It's actually my daughter, not a real pigeon. For many years, I work at Immunity and have done like so many different jobs, from like security researcher to manager. I've done consulting, I've done vulnerability and exploit research. And recently, I moved to Semmle that got acquired by GitHub no more than a month or two ago. And so here I am. I get back into my technical work and a full-time researcher. And part of the mission that myself and my team had is to try to help secure the open source landscape. So basically, part of my job is finding bugs every day. And generally do it on C, C++, and a little bit of code. Anyway, it's sort of funny to be doing a talk about open source security at a Microsoft conference. But definitely time have changed quite a lot. And if you look at that graph over there, you will notice that in 2017, the top 2 companies that contribute on open source projects were Google and Microsoft. And there is a reason for that, because definitely open source has won everywhere. Everyone is using, in one way or the other, open source code. However, there's many challenges with open source code. The first and foremost challenge is the code quality. There's this concept, very old concept, that there's many eyes looking at source code. And you can actually say that there's many eyes looking at binaries too, if you are on the offensive side of security. But the reality is that the whole idea of many eyes looking at code is not usually like that. There's certain projects that get fast and get reviewed quite a lot. But that brings us to our second problem, which is the supply chain. You might looking at, and as a company, especially the big ones, are able to, be able to review certain source code base, like the first layer, but there's always dependencies, and those dependencies have more dependencies. And so maintaining those supply chains is really, really hard. And it's a job that cannot be done by one company, but requires sort of like coalition of different companies working together in order to help secure the open source world. It's funny because I was doing this sort of like mental exercise, and I was working on a little bit of Golang. And if you ever work with Golang, definitely I'm not an expert, so don't quote me on this. What they do is, in order to import a library, what you do in Golang, you go directly and do import, and then you point it directly to the GitHub URL. So when you get the project, they will automatically download the different projects in GitHub of the libraries that you want to import in your own code. Now, what I thought is, like, let's imagine that I'm a adversary, and I want to get into some sort of like company that I know is using certain code base. So what I did is a little exercise, and sadly I didn't bring the image here. So what I did is I went through one of these big companies that works in, it's an application for transportation. I'm sure you know it, who it was, and they use a lot of Golang. So what I did is I took all the different imports and look at all the different GitHub projects that they were importing, And then I look at the different countries where the developer or the maintainer was from. So I thought, coming from Argentina, with our currency, I don't know if you heard, it's terrible. I thought, if I'm a nation state adversary and I want to buy one of those projects, I will go to the country that has the worst currency and try to buy that project. So I end up with a map, and what I find out is for those projects, there were developers from all around the world. So it's a sort of interesting exercise to see how you potentially attack that supply chain. And then there is a problem of CVEs. CVEs, it's necessary evil in a way. If you are working on closed source, especially for Microsoft and other big companies, CVE works pretty well. And the reason for that is because Microsoft and other companies has proper triage on the vulnerabilities that get reported. So all the information that you get from a CVE is the actual risk of the vulnerability. There's people in Microsoft that check that and see if something is exploitable or not, what is the potentially attack surface, et cetera, et cetera. But with open source, that doesn't really happen. And what happened is that you have a lot of different security researchers that sometimes are sort of playing the game of CVEs. So they obtain different kinds of CVEs. And let me tell you first, Mitre does an amazing job. But obviously, there are only a few people, and they get quite a lot of submissions. So what researchers tend to do is over-exaggerate the risk of the vulnerabilities, and sometimes the open source project doesn't have enough time to do proper triage. They only have time to actually patch the vulnerability, and so we end up with CVEs that doesn't really reflect the reality of the vulnerability. And you see that a lot. You will see on the news, the last pseudo vulnerability, and everyone is saying this is a terrible bug, but when you start scratching a little bit of the surface, you realize that the bug is not that bad. I mean, it requires a very customized configuration, so I mean, the risk is really, really small. And so the other problem that CVEs has, especially since it became the source of a lot of different automation tools, is that there are way too many. How many CVE updates do you think there is per week? Let me play a game of raising hands. So do you think that there's 100 CVEs per week? Raise your hand. Do you think it's something between 100 to 300? Do you think something between 300 and 500? Do you think it's more than 500? If I was a bad person, I would say that would depend on which week. If it's the second week of the month, you know what happened, right? No, I'm not talking about Microsoft. I'm talking about Adobe. I don't know if you have dirty minds in there, but I'm talking about Adobe. So the reality is that I work and I look at CVEs every morning, and what we realize is that every week there's around 300 to 500 different vulnerabilities. So it's really, really hard to control that amount of vulnerabilities being submitted into Mitre, which is sort of the problem. And of course, you have all sort of extremely bad things being submitted. So what you're going to see here, it's a vulnerability on a project called Borg Reducer. I actually talked with the maintainer. The bug, if you can see on the left, and I hope the font is big enough, it's a very basic string copy, string cat, right? But the problem is that this project is not a real project. It's someone create a project for some assignment at school. And if someone has to have a bad note, it should be from a professor, but not from Mitre. So someone submitted actually a bug in there. The sort of funny thing is how he fixed it. So what he did is transform the stack array into basically a pointer, but it was not allocated in any way. So it's sort of and I think that might be less vulnerable than the other one. If you think about it, depending on what's on the uninitialized variable, then maybe it's actually pointing to something that will not overflow. Sort of like a Schrödinger variable of some sort. Anyways, I mean, the point here is that they're being assigned CVEs to projects done by kids at school, that has no usage other than in class. But this guy basically created a repository, and someone look at the code and submit a bug, and then send it to Mitri. And for Mitri, it's really hard to see which are real projects, which are not. There's a lot of work involved in that. So, before we start talking about all the different problems that we had, let's sort of talk about some of the solutions that you can see currently being done. And one of the main ones which was really interested, and I'm sure everyone heard about that, is OSS Fast, which is basically continuous fuzzing provided by Microsoft. So Microsoft offered this for free for each open source project, and the only thing that you're required to do that is create a specific Docker file, and then every time there is a pull request, then Google will fuzz the project, and so you have continuous vulnerabilities fuzzing. So it's actually a quite interesting project, and I think I have more than 200 projects, and they find around 9,000 vulnerabilities. There's also this Syscal project from Google that they have been fuzzing the kernel like crazy. And I know because I have seen some of the results, the work they have done for USB is crazy. They find so many vulnerabilities on USB that the Linux kernel maintainers are not able to patch it as fast as they were submitting it. The other project that's very interesting in terms of trying to secure the open source work is the bounties. And this is sort of a double-edged word because there's a lot of different projects that are being paid for finding vulnerabilities, but some of the projects, sometimes they don't have developers that are getting paid. So the maintainer is actually doing for free on their own time, and there are researchers that are being paid for to find vulnerabilities. But in reality, the project is not really bad. I think it's a good idea. It helps. The objective, obviously, is to try to fight the black market, right? And obviously, fighting the black market is really hard because there's a reason why it's called a black market. It's always going to be more expensive or you gain more money by selling a vulnerability through the black market. Because the black market know they're competing against the white market, so they're always going to be a little bit more expensive, and that expense is going to be translated to their clients, whoever they are. But of course, if you are a researcher, and obviously you don't know what people are going to do with those vulnerabilities you sell to the black market, and you want to have a clean conscience, then obviously going through these boundaries is a really good way to do. In a way, the black market is like taxes, and you pay and you don't know what they're going to do with your money. Sort of like the same with the black market. So let me tell you a little bit of what we are doing. There's two things. There's a really interesting project that GitHub have, which is called Dependabot, and what they do is basically a bot that looks into your open source project, and what it does is it looks at the different dependencies that you have on your project, and if there's any other dependency that has some sort of vulnerability, they will let you know, and they will let you know how you can fix that, and if you want, you will be able to fix it. This sounds simple, but it's so useful. And the very interesting thing about this is that it's very simple to use it. And so in a way, and it's part of our mission, we're sort of trying to democratize the access to security. It doesn't have to be just for security researchers. The developers should be able to access those tools without having to learn a lot about them. The other thing that they're doing that's very interesting, I don't know if you ever submit a vulnerability to a vendor, is they have these security advisors that you can enable in your repository. And it's quite interesting because finding the right security contact sometimes is so painful that you end up deciding not to submit a vulnerability because it's you sending an email, nobody ever answers you, and so go and say no. So the solution for that is they have a private section that you can send a report, and it only goes to the maintainer, and it's not going to be public in any way. So it's quite interesting. The other thing that I think is very interesting is the donation part. You can sponsor an open source project, but not for researchers. you can sponsor it for the maintainer. So in a way, like if you want something fixed, you can actually help with some money to the project, and obviously that helping with money also tend to translate into having better code quality. And let me tell you what my team is doing. Aside from like finding vulnerabilities, we're doing a lot of like variant analysis. Have you ever heard of variant analysis? All right, so let me explain a little bit of the concept of variant analysis, and let's go with the corollary of the presentation. The idea of variant analysis is that vulnerabilities never came along. So there is always, if you find a vulnerability of certain bug class, there's always going to be a similar pattern in the same code base. And sometimes that pattern can be moved to one code base to the other. So QL, it's an amazing tool that was designed by a lot of really smart people in Oxford. And what it does, it basically compiles a code base, and it transforms it in some sort of like relational database or customized relational database that we call snapshot. So later, what you can do is you actually create queries in a language similar to Dalalog, or like in a way it's sort of like SQL. So you can create an QL query where you sort of like create a bug class based on that query. So that query will define a bug class, and then what you will do is you run that query on the database, and instead of finding that specific bug, you will find more than one bug. And I'm going to walk you through some of this process over here with different bugs that we have found in the past. So what we do with QL, we are not only doing bar analysis, but it also helps you to explore the code base to find like different leads. This is lgtm.com, which is part of the same project. lgtm.com, I don't know if you heard, but what it does is a website that you can point out to whatever open source project. Before I say that, QL is free for open source projects. So you can download the Eclipse plugin, and you can run your queries on the code base, and it will work perfectly. Not in the code base, in the snapshot. So lgtm.com, what it does is you will point out to whatever GitHub project you have, open source, and then what it's going to do is going to download that, it's going to compile it, it's going to create a snapshot, and then it's going to run a series of different static alerts or queries that we have predefined, and it will find vulnerabilities. And if you enable the PR, it's going to actually send a message to the project saying, we find this bug here, this is how you can look at the bug, and then later you can fix it. So we are doing that for any open source project that decides to be part of LGTM. So and this is sort of like a paper that I recently found out is very interesting. And it's a work from a couple of people from the University of Iran. And what they did is, and it's sort of funny that what they did, so they went to Stack Overflow and start finding different examples of snippets that were vulnerable. And then they took those snippets and started looking at different projects on GitHub. So they find 69 different snippets, and they found around like 2,000 projects that were reusing that Stack Overflow snippet, and it was actually vulnerable. Raise your hand whoever used Stack Overflow to write something. Here we go, yeah. And everyone is not raising a hand, they're lying, so. So it's a very interesting project, and it's sort of like our way of thinking when we are doing all this work with variant analysis. So I want to, like every good talk has analogies, so I've been thinking like, what's the best analogy for my talk? So in a way, it's sort of like the coffee cherry, right? So when you're writing a query, it's gonna, the query is gonna be very generic at first, but then as soon as you start peeling it, and you go through the different parts of the cherry, the berry skin, the pulp, you end up finding the right bean. And obviously, this makes no sense right now, but I'm sure it's gonna make sense for you in a little bit. So let me start with the first one. This is sort of like a crowdsourced vulnerability finding or example. It's sort of like funny. It was on like, I think my first month in Semmle. So I was I was doing, and I do that every morning or every 2 or 3 days, is I sit down, I look at all the different CVEs that happened that day or the day before, and what I do is I try to triage that. So what I do is I look at the CVE and I write a query that model the bug class that was sent as a bug to CVE. And then what I did was I wrote a query defining this specific vulnerability that I found, and I ran it on the Linux kernel. The query that I generally write is not that good, especially that one because I had been working for a month, and QL takes some time to learn. So it was not really good. But what I did is I tweet and say, this is the query that I did on the Linux kernel based on a vulnerability that someone already found. And it's give me a couple of, I think it was 1,000 different results. So you have to go through 1,000 different different points in code where that sort of bad class was in there. And the funny thing is that Tavis actually looked at my tweet and started going through those thousands, because it seems like Tavis never sleep. And so he actually found a vulnerability. So this is the sort of the bad class. And it's not really, by itself, it's not really a bad class. So basically, it's a condition that has an array, and that array is being assigned a value on that loop. It's as simple as that. The way you do it in QL is that if I have to think about how we'll find that, I will be like, I'm going to find a loop that has an array, which is an index, and something gets assigned to. The way you do it in QL is a little bit different. So you're actually looking at a variable that has an index, and that variable is of the type array, and that is being assigned. Something is being assigned to that variable, and at the same time, that variable is part of the loop. You're not looking for the loop, you're actually looking for the variable inside the loop. So this is sort of the way of thinking when you're writing QL, or at least for me. And so the bug ended up being a bug on a monitor, so it's not really good. But if you're going to a conference and you plug your computer in a monitor, and somehow it's an evil monitor, you end up with your computer own. So maybe don't give talks in Russia or something. I don't know. It doesn't make any sense. But the vulnerability was there, and it was hilarious how the whole thing works. And this is sort of the timeline. I make that tweet, Tavis find it, and then a bug was reported and was patched. So it's sort of hilarious as a first example. The other big example, and this is really good because it's going to help us sort of work into the mindset when you are trying to find or working with QL, is this U-boot. First of all, and I forgot to say, originally I was planning to give this talk with Fermin Serna, but he has other commitments. He couldn't make it. So, and U-boot is part of the research that he had done. So, I don't know if you heard about U-boot. It's a bootloader that is being used by a lot of different devices, surprisingly. Kindle uses it, Chrome OS on ARM uses it. There's a lot of IoT devices that also use U-boot. And obviously, any vulnerability before the signature check is a potential jailbreak. So you can potentially attack it through a file system. And obviously, if there are any network issue, it would be very interesting to trigger. And so let's get into U-boot, which is going to be terrible. Just telling you. So this is sort of how you work with QL. You first start with a seed, and that's where the cherry thing sort of start making sense. You start with a seed. The seed is sort of a pattern you're looking for. And then you write a query that defines that pattern. And then you do triage. You go through the different findings that query gets you. And then you realize that it might need some work. So you refine the QL query and start again and start again. And there are different types of queries, as I was saying before. There's a query that will find potentially places where a bug will be. And that's the sort of queries that I'm able to, or I'm used to do. And then there are queries that are very precise and have 0 false positives. And this is the sort of query that we put on LGTM or any CI/CD in order to find a bug that is as precise as possible. But to me, I don't want to find a bug that is, I mean, obviously, find a bug that is precise as possible and find a bug right away, it's amazing. But in general, I'm trying to explore different things. So something that is generic but not goes as crazy as finding 1,000 different places, for me, is really good because I'm learning from what I'm finding and I'm refining my query to get better and better every time. And there's like different levels of query. There's queries that are very generic and find a lot of different things. There are queries that are specific to a code base that finds vulnerabilities. And then there are the best queries, which are very precise, but also they're not tied to a specific code base. And we will learn a little bit more about that. So this is our seed. So we were looking at code, and what we realized is that there is a bug, actually 2 bugs, in the code of NFS on U-boot when it tries to boot over NFS. And I don't know, see if I have, here we go. So the bug is basically taking something directly, which is a LAN, directly from the network, and then in those 2 different places is using the erlang, the variable that was signing directly from information that was obtained through a packet into the size of a mem copy. So that means that we control the size, and we also control the source. So it's sort of like a very good bug if you want to overflow something. So we have that bug, right? That's the seed that we had. So the most generic thing that you can write is this query over here. So remember that I was saying it's sort of like SQL. So you have like from, which is how you define the different variables that you're going to use on the query. And the where is where you start like filtering what you're looking for. And then finally, select will tell you what you want to see once you find what you are targeting. So in this case, I'm saying I want to find a function call which name is call. And I want that function call, the target of that function call is going to be of name mem copy. And obviously, you're going to be like, I can do that with grep. Of course, you can do that with grep. We're talking about a very generic query. It's going to get complicated as we go. So that's the most basic query you have. But let me go back to code. So as you can see here, what I was looking for is basically the mem copy. There was like 2 points for this vulnerability. One is that when the actual vulnerability happened, which is the mem copy that I have the latent and the control, and the other part is where the actually erlang variable is being assigned. So what I was looking on my first query is basically when the vulnerability is being triggered. The problem is that if I'm looking for all the mem copies on U-boot, I'm going to find a lot of mem copies. The other interesting thing is, like, let's find when that field, which is reply, is being used. So now I had, when every time that field is being used, I'm going to find the exact place. I mean, it's not perfect, but now I know all the different places where I could potentially have a vulnerability or where I have control of the network. Or sorry, of the content of the network. And this is a very interesting phrase. Given a problem-specific set of source and sink, is there a path in the data flow graph from the source and from some source to some sinks? This is basically defined data flow analysis. The good thing about QL is it has a data flow analysis embedded into it. So, and if you think about it, a lot of different vulnerabilities can be defined as a data flow problem. There is a source where the input is coming from, and there's a sink where the actually function is being triggered that triggers the actual vulnerability. And there are many like different backlashes that we can, obviously not all of them can be defined that way, but it's a good way to think about it. And a big percentage of your vulnerabilities, we have this sort of like idea behind it. For example, if you talk about like SQL injection or across the scripting, there's a point where there's a user input get it into the program, and then the sync will be either the function is being used to show that data into HTML, or when it's being queried into the database. So let's start with the first real query. As you can see here, and don't get lost with that, it's not that hard. What we're doing is that we are redefining the data flows class. You have to do that every time you want to create your own data flow. And what we're going to see here is that we have to override two different methods inside our data flow. One is source, the other one is sync. The source is obviously going to tell us which is the source of the potentially bad class that we want to define. In this case, what we're doing is that we are trying to find a field that's being accessed. And so source is obviously the definition of my source. And so I'm going to assign it to the field access. And what I'm going to say is, I want to find an access which target is this field, and the name of this field is going to be reply. Might be a little bit confusing, but that's sort of the idea. This is the source. So basically what we are doing is we are looking for a field that's getting access, and which field name is reply. Now, on the other side, on the sync, what we're going to do is we're going to look for a mem copy, which sync is going to be an argument. Which argument? The third argument. In this case, 0, 1, 2. 2 is basically the length of the mem copy. So this is what I find. And this is the part we're actually doing the query. And we're saying that the query has flowed between the source and the sync that we just defined. And we find, first of all, we find the two vulnerabilities that we already seen. That's the first thing we view, because obviously you have to find the same vulnerability that you were defining your back class with. And then we start finding other different things. This is quite interesting. As you can see, there is the reply field being accessed to the file h3 length, and then it's being used in memcopy. There's a comparison being there. The problem here is that it's signed. It's a signed integer, so you actually can bypass it easily by doing a negative number. Now, how you exploit it is a little bit more complex, but this is one more vulnerability to the list. And as you can see on the left in there, there's a counter of the different vulnerabilities that we were finding as we were working through this project. The other thing that we're looking for, this is a very interesting example, because as I was showing before, we were always working on the same function, right? But with QL, you can actually do data flow analysis through interprocess. So what happened here is that the actual error is happening on this function NFS read reply, but the actually mem copy, it's being triggered on store block. Store block is the actual mem copy that has the error. So it's quite interesting because now we are not doing just data flow analysis on one function, we're doing it globally through like different functions. And when you start doing that, it's sort of like magic, the kind of things you can find. There we go, I have arrows, that will be easier. So let's expand the query a little bit more and even make it at the point where it's more generic, that you can use it on a different code base. So what we did, and you will notice that on the different vulnerabilities that we found, there is a pattern. And network to host was being used on most of the, basically on all the bugs that we find so far. So this is the part where you are learning about the findings you're getting, and then you're redefining your query to make it even more precise. And so what we're going to do is, instead of going for the reply field, we're going to look at every time that a call to entol, entol-s, entol-ll is being used at the source, and the sync will remain the same. The sync is going to remain being the mem copy, the length of the mem copy. So the interesting thing about that is that now we're not making the query depending on the actual code base, but rather it's going to be generic. And we can use that query for other code base, because basically you're doing like every time that function entos, it's actually not a function in Linux, it's a macro, which is why instead of having what we used to have, the function call thing, we're actually having the macro invocation. And then like we can even expand it even more, like instead of looking for mem copies, we can start looking at other functions which has a size, and use it to do that. And then we start finding other vulnerabilities. This vulnerability is not really related. Well, yes, it's not really related with the query that we did, but it was quite interesting because if you make IP UDP len less than UDPR HDR size, then you will be overflowing and find two more of those vulnerabilities. And then this vulnerability over here. It's quite nice because it's like a plain Stack Overflow, and we find this vulnerability in 4 different places. And as you can see, very straightforward. You control the packet, you control the LAN, and the overflow happens. And it's funny because this U-boot is being used quite a lot. Then this is the other one, which is a read OOB. And in this case, basically, if you size off is if you make packet less than size of the size of reply, then what's happening is going to be actually doing an information leak and writing on data information that is not supposed to be writing. So in the end, we end up with around 13 different vulnerabilities. And to be honest, it's quite interesting because we start with a seed and we start creating a query. And now that query, we're using that query for a lot of different projects because it's very generic. And let me show you a little bit of another project that I have been working, and it was on the Linux kernel. In this case, what I was doing is, again, every morning I look at all the different CVEs, and I find that interesting CVE on the Linux kernel is actually 2 different vulnerabilities. And as you can see, this function CFG802011 find IE is a function that basically obtains the information element of a wireless packet, and it returns exactly where that element is on the whole beacon or the whole frame of what we are looking for in Wi-Fi, and then it uses the len directly into a mem copy. The only problem is that len is a 1 byte long. So you have to be very sure that the destination is less than 255. So as you can see here, that CVE actually represents, I think there was an extra one, but represents at least 3 different vulnerabilities that has the exact same pattern. When I look at that, I was like, I have to make a query, because if there's 2 cases, it has to be more than 2 cases. So just to give you an idea of what is an information element, so there is a sort of like fixed part inside 802.11 frame, for example, on a beacon. That's sort of like a fixed part, which is like frame control, the duration, the BSS ID, et cetera, and there is a sort of like TLB elements, which call information elements, which is the one that we saw, that has 1 byte long EID, which basically defines the type of information element that you're looking for. Then there's 1 byte long length, and after that is the actual data. So I thought I'm going to write a query that, in a way, if you look at it, is super similar to the one that we look on the U-boot. But there was no relationship with this vulnerability and the other. So what I did is like, find me a source that the source is actually the result from a call to FG8200 find IE. It's hard to talk about those functions names in public. Anyways, find me that. And obviously, the sync of the data flow is just the normal mem copy. We're looking for the 3rd argument of mem copy, the length argument of mem copy. So I look at that, and I couldn't find anything. But I thought, why don't I look to a different similar functions that I know the kernel has that obtain and work exactly the same way. There's so many of those get IE functions in the kernel. I would say around like 8 to 10. So I started looking at them, and I wrote this the exact same query. The only difference is that the name changed, and I'm not gonna pronounce that function name because it's way too complex to do it. And so the same thing, you get the result out of that call to that function, and then as a source, and then as a sink, you have mem copy the third argument. And so I look at that and find this example in here. What you can see is they're trying to obtain the SSID of, for example, a beacon packet. And this is on the CW 1200 wireless driver. And what it's saying is that it's obtaining the chunk of memory from that specific IE, and then it's passing directly to mem copy. Again, like the syncing here, it's extremely simple. I'm just looking for as a sink, but I can do way more complex things than looking for the length of a mem copy. Even I can make it like more generic to look for like mem set, mem move, but even I can make it to other things. I can actually define the concept of a loop on the back class and say like, is this the size being used on a loop, et cetera, et cetera. So again, this is very simple, and the good thing about this very simple is that it's really good to show it to you if you have no experience with QL. This is one of them. This is another one in here. This is on CF 802011WX compat for managed mode. The exact same scenario, exact same. They're even actually looking for SSID as the other one. It can mean like many different things, but those cases were the same. And as you can see here, this is even more clear. It's obtained a pointer to where the IE is, and is using the second byte, which is the length, as we learned before, as the third argument of a mem copy. So this is how it works in terms of the timeline. It's funny because, as I said before, every morning I wake up and I look up CVEs, and that's what happened. Like the person, Han Gun, reported, or at least it was public on the August 28th. On 29, I was writing the query. On the 30, I reported 2 bugs. And, well, it takes a little bit more for Linux to actually fix it. But as you can see, it was fine one day. I wrote the query. I reported the next day. And you know, it was that fast. And there was a couple of bugs. And obviously, this most likely actually reported more than those. And some of those other bugs that I reported were actually being handled before that. There was a lot of like SSID related sort of like similar backlash, but some of them, the SSID length was controlled before that, and you cannot see it when we actually find the query. So these are actually the two that were actually a vulnerability. So there's a lot of different work that is left specifically with those IE. Surprisingly, that's a really common bug, and there have been similar bugs as this one in the past. So it's not the first, and probably it's not going to be the last. But an interesting thing is we can use QL, and everyone can use QL on open source code, so we don't repeat ourselves. There's a phrase from Marx that says something like, history repeats itself twice, first as a tragedy, and second as a comedy or as a farce. Sort of like the same thing can be said about bugs. Like we don't actually learn from the bugs that we found, then like it will repeat itself, but this time it's going to be comedy because like, you know, people will laugh at us for not finding the bug that, or the pattern that we already, the bad pattern that we already did. And so finally, I recently, like last minute, find a last bug, which is in a way similar to that, but it's not really on IE, it's on Wi-Fi Direct. So very briefly, because I have only 1 minute. So you have the IE, and inside the IE, there's a vendor-specific IE. So Wi-Fi Direct, I'm sure you heard about that. It's like sort of like P2P Wi-Fi communication. They have a funny like TLV similar to the IE, But the funny thing about the TLB, it's inside an IE. So it's like, it's a piece of memory inside IE. And the funny thing about this TLB is that the length of the Wi-Fi Direct TLB is actually a short. So it's encapsulated in a byte-long length, but inside in there is actually a short. So like, makes no sense, but somehow is in there. What happens here is, as you can see, your NOAA len is being taken directly from the network, and that byte in here is only checking that it doesn't go beyond the end of the whole frame. But the interesting part is that in this loop over here, it's actually going through NOAA len, and what it's doing in this case is copying. Like, we cannot see because I put that message in there, but it's copying it into the different types, and these types are like 2 bytes long. So I can make that NOAA length more than 2 bytes, and there's going to be an overflow. And this is on a real tech driver, which is quite interesting. And it can be triggered by a beacon, but it has to be a Wi-Fi Direct beacon. That being said, thank you very much. If you have any questions, I'm going to be around.